Hey everyone, welcome to the lecture on kinetic concepts of analyzing human movement. So, some of the things in this lecture are kind of repeats of things we've covered earlier in this course, but they're good to go over as we move more into the biomechanics side of this course. So, with this, there are some things that you can access this PowerPoint and kind of pause the video and kind of review some of the things we had talked about in some other lectures. So feel free to pause the video and just quickly think about these, go back to making sure you understand these particular components. And then, of course, you've got your learning objectives. And so we want to go ahead and talk about some of the basic concepts related to kinetics. And so one of those is inertia. And so we're going to go through quite a number of terms in the first half of this particular presentation. And so just defining them, trying to describe what they are. So the first one's inertia. And so that's a tendency of any body to resist a change to its state of motion. So if an object is sitting still, it wants to continue to stay sitting still. If it's moving, it wants to continue moving. And so everything when it comes to movement wants to resist being changed. So that's what we kind of look at with inertia, but there's always things acting on any object that are trying to change its motion. So realize that when it comes to inertia, that's directly proportional to mass. So the more massive an object is, the more it tends to maintain its current state of motion. So a car we can move relatively easily. Like any of us could probably roll a car, especially if it's on some flat ground. However, a mountain with much more mass is almost impossible for us to move the entire mountain. With inertia, there's no real units to inertia. It's more the way we talk about things. And so, an example of that is a weight bar will stay in place in the absence of being lifted because of its inertia. Especially again, if we got to think about what a force is as well. So, a barbell will stay in place on flat ground, but if we put it on a hill, it's going to tend to roll down because of gravitational forces moving that. And so that's one thing to kind of keep in mind. So related to that, we already brought it up in the last thing, is we also have mass. So we talked about inertia being related to mass. So what is mass? It is simply the quantity of matter that is composing a body or an object. So how much matter is actually making something up. So how much matter is there in a dog, in a tree, in a desk, basketball, you, et cetera, et cetera, et cetera. Typically, when we look at mass, we represent that by the letter m. The lowercase m is talking about mass. And a typical unit that we see for mass is kilogram. So in the metric system, our mass is through the kilogram. And so we sometimes call that your weight, but your weight is different than your mass. And so the chart here kind of expounds on that a little bit. And so when we look at that, mass is that quantity of matter, where weight is the force by which basically gravity is pulling that object to the center. And so they are related, but they're not the exact same. So mass does not always equal weight. On Earth, sometimes we do see that because we refer to things as having a weight in kilograms, but that's more referring to their mass. And that weight portion would change if you went to something like the moon or a different planet or went into space, but the mass portion would actually stay the same. And so there are different ways to kind of look at that as you go through. So next we have force. So what is force? And we're going to start combining these terms as we go through as well in different examples. So force is simply a push or a pull acting on a body. So you got the example, you can push or pull something. And so it's when we're talking about force, there's different components of the force you have to look at. You have to look at the magnitude, so how much force is being applied. You have to look at what direction the force is being applied, and where is that force being applied. So at what point is the application. So when we look at force, force is typically signified as a capital F, and that is equal to mass times acceleration. So m times a, mass times acceleration. The SI unit for force is typically denoted as newtons. And so when we talk about weight, we're typically talking about more of this force, gravity pulling down on a mass. And so if we go back one, if you notice there in the diagram, when the person's on Earth or when they're on the moon, they're newtons. So that's signified by the capital N there. newtons change depending on whether they're on the Earth or on the Moon, but their mass, kilograms, stays the same. And so when we're talking about that weight scenario, that's the force we're looking at is gravity, but it could also be a force we apply to moving a box across a floor. So with force, we also have to look at what is called net force. So net force is basically the resultant of multiple forces acting on an object. So what is the overall outcome of multiple forces acting on an object? So an example of this would be, think about you standing on the ground. You have gravity pulling you to the ground. But if you want to get off that ground, you can jump. You can use your muscles to force yourself off the ground. And so what you're looking at there is two forces acting on each other, and then what is the result? If you don't have enough strength in your legs to propel yourself off the ground, that means you couldn't produce enough force to overcome gravity. If you are able to, your force that you generated was greater than gravity, and so that will determine how much greater that force was, will determine how high you jump. And so net force is looking at all the different forces, all the different places that force is applied, the magnitude and the direction. And so when all those forces are balanced, they cancel each other out, and the net force is zero and no change is occurring. When those forces are not balanced, typically something will occur. And so the example picture is tug of rope or tug of war. If both teams are balanced, both stay the same, nothing occurs. But if one team happens to be able to apply more force, then we have a net force in their direction, and you should pull the other team towards you. So with this force and this net force, part of the calculation that goes into that is what we call the center of gravity. And so the center of gravity is a point at which a body's weight is equally balanced. No matter how the body is positioned, there's a point in your body or on an object where the mass is equally balanced. And so a way to look at the center of gravity is to take like a pen or a pencil and put it on your finger and see if you can get it to balance. Okay. Once you've got it balanced, you have found the center of mass, and no matter that position, that is still the center of mass for that particular object. So center of gravity, center of mass, those kind of go back and forth. They're used synonymously, and so I did it already when we were describing it. So in a body, so in our bodies when we're looking, or any body that's moving, the center of mass or the center of gravity is an index for body motion. So how is it going to move? It's a good reference point for what it's going to go around and what's going to determine that movement style to some extent. And so the location of that center of gravity is also going to determine how we react to external forces. If someone's pushing against us or things like that, depending on where our center of mass is, our center of gravity, can change how our bodies respond to that external force. So then we have pressure. So pressure is simply a force per unit of area. So pressure is still looking at force, but we're looking at a particular force applied over a given area. And so usually it's about the force that it acts. And so the way you calculate pressure is dividing the amount of force that's applied over the area. So if we apply a certain force and we cover it over that area, we can determine how much pressure is occurring. So this is a lot of times used to describe force distribution. So how much force is being distributed across something. One pressure you may have heard of would be like pressure in your tire. So PSI, so pounds per square inch, is the way that looks. And so we can actually measure the pounds per square inch of you standing on the ground. So we can take your mass and the force that's acting on you, gravity, and how big your feet are, and we can look at how much PSI or pounds per square inch of pressure on the bottom of your feet. And so that's one way to kind of look at this. So you see the example of the person with the balloon pushing it into nails. Well, the reason that balloon hasn't popped is because what's happened is there's a large surface area of nails, and so that pressure is very minimal at any one spot. However, if there was only two nails right there, the pressure would go up per nail, so there would be more pressure at each nail, or the one nail or the two nails that are there, and so then that would cause enough to break the surface of the balloon, causing it to pop. So then we have volume. So volume is the amount of three-dimensional space something occupies or a body occupies. So the three dimensions are width, height, and depth. So those are the three things we're looking at. And the big thing with volume is objects can have the same volume, but differing weights and differing masses. And so we have to look at these separately, but they do play in a role in how things react and how things look. So remember, volume is how much space is taken up, and then we have different weights or we have different masses. And so an example of where volume comes into play is overheating can be a problem with anything you do for a long time, like marathon runners. And so marathon runners that are and thinner, shorter runners, since their bodies have less volume to create heat, so they literally are taking up less space. Uh, they have um, they have less volume that they're making this heat, but they have a relatively large surface area compared to their volume, and so they're able to dissipate the heat more. Someone that has a large volume and the surface area to volume, so you can see how we're starting to combine different things to do with pressure and other things like that. So if the surface area to the volume is we have a large volume to a low surface area, it's really hard to dissipate heat, tends to be held in. And so um, that's one way to look at those. And so continuing on this looking at the volume, we take a shot. So I know a bunch of you, college students are thinking, ooh, shot, not the type of shot you drink, but like a shot put used in the Olympics and a softball have pretty similar volumes. They're almost the exact same size. They almost take up the exact same amount of space. But a shot has a much greater mass. Okay, there's a lot more material in a shot put than there is in a softball, and therefore the shot has a greater density, and because of those things and gravity, it weighs more. Okay, so there's greater weight um, in proportion to its mass. And so the shot also has a greater weight and therefore a greater specific weight. Okay, so when you're looking at those, even though the volume is the same. And so this is the way we kind of look at this volume is things can have the same volume in different masses, different densities, and different specific weights. And so that can make the way we use them and the way we act on them a little bit more different. We all know if we were to try to throw these, it'd be much easier to throw the softball, and that's a relationship to those forces that we're able to generate as well. So with force, we talk about force, and usually when you're talking about force, it's in straight lines. We really aren't talking about um, any kind of angles. And so once we start adding an angle, so think about a circle. If we're moving something in different angles, we start to talk about that force as torque, or capital T is how you'll see it referred. And so torque is the rotary effect of a force. So how much are we kind of turning it on an axis? And so there are angular equivalents to linear force. So instead of pushing something in a straight line, if we're trying to kind of rotate it around an axis, we start to call that torque over force. But the concept is still the same. We're applying some type of motion to that in a more of a circular motion, okay, in more of a rotary effect. And this is also called the moment of force. So you guys, I would encourage you to watch this torque science of NFL football. It really does a good job of explaining this moment arm, but it's talking about how there is a spot that force is applied and an axis of rotation. And so this moment arm of how we can determine uh, how much force is being applied more in a linear fashion to be able to do the math around it. And so that's kind of what that's looking at. It's a great video to watch. Access the PowerPoint, watch that, or you can simply look up torque science on an NFL football, and you should find that relatively easily. So we then have impulse. So impulse, again, a lot of this relating back to force, is the product of force and the time over which that force acts. So how long is a force being applied to something? And so the impulse momentum theorem explains why follow through is an important aspect of many sports in basketball, baseball, boxing. And so, for example, a baseball player hits a baseball and follows all the way through the bat. The ball is in contact with the bat for a much longer period of time. So the force is being applied over a greater period of time, and we see the ball go further. If someone does like a check swing, and just barely for a very short moment of time makes contact with the ball, we tend to see that the ball doesn't go as far. And so that's because that force wasn't able to translate into the baseball as much. So the longer we can spread that force over time, the more of that force can be transferred to the ball, allowing it to go further. So this is a really good chart to kind of pause and maybe look at, but it shows you kind of this how we look at work, energy, and power, and how they're separate but also different. And it gives us things like what is work and talks about that. But um, work is done like whenever there is force is used to move something. So like opening a door, lifting groceries, things like that. And energy is the ability to do work and the ability to exert force. And so we're talking about how they're separate. Energy is separate. So work is actually doing something. Energy is the ability to do that work. And then power is that work over time. So how much time is it taking to do that work? And how quickly are we able to do that work? And so then it goes on to kind of draw these lines and to say, well, how are these the same and different? Well, when it comes to running up a set of stairs or walking up a set of stairs, it takes the exact same amount of energy to walk or run up the same exact flight of stairs, and it takes the exact same amount of work to do that. However, when it comes to power, if we run up that set of stairs, it's going to take a lot more power than it is to walk up those stairs because we completed it in a shorter amount of time. And so you're able to start making this connection of how is work, energy, and power the same, but also different. So we do want to apply some of the terminology. And so to do that, we're going to look at spiking a volleyball. So think about that motion and what that looks like. So someone spiking a volleyball. With spiking a volleyball, we have to take into account gravity along with our force. And so in a volleyball spike, you are applying, there is a force exerting downward on the ball. So the ball is up and there are forces being exerted in a downward force to that ball. And so with that, our arms may apply that force in a downward motion, but we're getting some assistance from gravity. Gravity works to our advantage because it's a downward force. It's pulling the ball down as well. And so to spike a volleyball, it actually doesn't take a tremendous amount of exertion for an effective spike. Most of them can be done over a very short amount of time. We don't have to build up and transfer that because gravity is helping us all the way down. And so that's really good because we're able to use some of the forces to our advantage so that we don't have to work as hard. And if we add a little bit more power, then we kind of see that effect a little bit easier. But additionally, with that spiking of the volleyball, if we talk about the work, we're talking about the force that's moving the object. The force in this case is going to be us, the person who is spiking that volleyball, and the forces we're able to generate um, with our muscles, and we're acting on the object of the ball. And so our force is going to kind of determine that direction of the spike, along with knowing that gravity is also pulling it straight down. So we kind of hit it at more of an angle than straight down a lot of times because, well, we don't want the ball to go straight down where it is. So when it comes to that, we're also looking at velocity. And so it's the speed of movement. How fast is that going? And so that's how much distance is it covering over amount of time. And so we know with a volleyball hit, usually we're trying to get a very high velocity because it's tougher for the opponent to be able to react, right? So there's reaction time that goes into this. And so the higher the velocity, the tougher is the spike. For them to be able to get in position and try to block it or recover it to get it back over the net. Additionally, part of that velocity is acceleration, which is how quickly are we changing that velocity, that increase in velocity. How quick is the acceleration and that velocity going from slow to much quicker? And so there's lots of different strategies when it comes to acceleration. So if we increase the amount of force that we apply to the ball moves faster, it accelerates faster. And this can make it hard for opponents to kind of react to, like we talked about in the last one. But there are also times when spiking a volleyball, we decrease that force of the spike, becomes more of a lob. And usually that's more about putting it in a specific placement where maybe a defender is not. So the acceleration, changing of speed is slower. The overall velocity is probably slower because we're not trying to get them to not be able to react, they're already not in that position. And so we want to be able to control it a little bit more to get it exactly where we want it. And so you're starting to see this relationship between accuracy and velocity, or accuracy and acceleration. So if we want to put it in a specific spot, we usually have to apply a little less force. So related to that spiking of volleyball, there are Newton's laws, which we've already talked about in this course. And so there are three of Newton's laws. And the first one is an object at rest will stay at rest. An object in motion will stay in motion unless it's acted upon by an outside force that is greater than whatever it is currently doing. And so examples of that is if you spike a ball into the net, the net is the unbalanced force and it stops the direction of the ball. Or if someone blocks a spike, the blocker's arms, their forearms, acted as the unbalanced force that stopped the ball, changed its direction. Again, looking at these from the eyes of spiking a volleyball. Second law is the acceleration of an object is dependent on two variables. That is the net force. So think about net force that we talked about acting on the object, and the mass of the object. So force and mass are related. And so a spiked volleyball creates a net external force, so sum of all those forces, and it stings your hand when you stop it. So if you're blocking that, it hurts your hands even more, though, if that ball is hit by a stronger opponent. So again, think about if you're blocking a volleyball spike, it stings your hands, it takes some force to stop that ball. But if someone provides more force, more velocity to that volleyball, it has the same mass, it stings more because there is more net force going into that. And so that's kind of that concept. And then the third law is every action has an equal and opposite reaction. So when the force of a spiked ball meets the reaction of a player's block, we know that that ball changes directions. Okay, and so there's force applied in your hands. They kind of come back a little bit. Usually, the mass of your hands is a little bit more than the ball, so they come back just a little bit, and then the ball changes direction and goes back. And so you're seeing equal and opposite reactions. If we summed up those two movements, their velocities, their forces, they would actually come together to what it was before the volleyball struck your hand. So the ball tends to move slower after it strikes. Another example of this is if you have a hard force has more force than a soft volleyball, or says more force, also has more mass at the same time. And so the ball bounces off the court in an equalized reaction to that impact. So it hits the ground. There is some force there. The ground moves slightly. The ball bounces back up. There's an opposite reaction, and it moves a little bit slower because some of that force is transferred into the ground. And so these are the three laws as looking at volleyball spiking. And so what you should do now that we've kind of talked about this is pick to apply some principles of physics that we have just discussed, kind of like we just did, and apply them to a specific activity or a specific motion in some activity. And so there's a list of topics to choose from, and then there's the situations to address. And you should be able to walk through all of these things with something like a deadlift or a tennis serve or walking on a balance beam or things like that. So do that, and you'll apply this information and just